So we have learned in this module that circular motion is caused by centripetal force. And that centripetal force can have as its source one of three things, at least in this initial level of physics that we're talking about. So one source of centripetal force could be the tension on a string or the tension on a rope from when you're twirling something in a circle. The second source for that centripetal force could be friction, such as when you have a vehicle going around a curve on a road. And we've learned that the third source of a centripetal force can be gravity of a very massive object that is going to cause circular motion. And so that circular motion, if I have a very massive object, could be a planet orbiting around the sun. It could be a moon orbiting around a planet. And so again, very, very massive objects. And so we're going to kind of combine everything that we've learned here in this final section where we're talking about orbital motion. Now, in example 7.6, we are asked to calculate how fast Mars travels in its orbit around the sun. And so what we have to analyze here is all of the forces that are at play. So if Mars is orbiting around the sun, it is the sun's gravity that is causing that rotation to happen. So I know that the force of gravity from the sun is equal to the centripetal force. Okay? What do I know about each one of these? Well, I know that gravitational force, if I use Newton's law of universal gravitation, I know that I have the gravitational constant times the mass of Mars times the mass of the sun, all over the distance between them squared. Okay? I also know that centripetal force, when I'm looking at the object that is in circular motion, this is going to be the mass of Mars times its velocity squared over its distance from the sun. Now, if I look at that, what I can see is that I have the mass of Mars on both sides. And so that is actually going to cancel out. I also have distance from Mars to the sun on both sides. And so one of those is going to cancel out on this side, and it will cancel out completely on this side. So if I neaten this up, what does that look like? Well, I have the gravitational constant times the mass of the sun over the distance between Mars and the sun is going to be equal to the velocity of Mars squared. Okay, much simpler equation to work with now. So let's go ahead and plug these numbers in because I do want to show you how the units work in all of this. So gravitational constant is 6.67 times 10 to the minus 11th. Newton meters squared over kilograms squared. Remember that constant has really, really strange units to it, but you'll see why here in a second. The mass of the sun is 2.0 times 10 to the 30th kilograms. And then the distance is 2.3 times 10 to the 11th meters. And I know that all of that is equal to v squared. So let's look at my units here. This kilogram is going to cancel with one of these kilograms down here. A Newton is a kilogram meter per second squared. So the kilogram in the Newton, if I even take out this Newton and I make it a kilogram meter per second squared, then this kilogram is going to cancel with that kilogram. This meter is going to cancel out with this meter, and so what I'm left with is meters squared per second squared, which is what I should have for velocity, because I'll take the square root of it and then I'll get meters per second. Now, you don't have to write that out every time and do it, but I did want you to understand that yes, these units really do cancel. So now when you plug those numbers in and you take the square root, you're going to get a velocity of 2.4 times 10 to the 4th meters per second. Okay? Now, from here, they then ask you to calculate the period. So in other words, how long does it take Mars to go all the way around the sun one time? So first of all, first thing that I need to know is, well, how far is the distance around there? So I'm going to have to know the circumference of the orbit that I'm talking about, which is 2 times pi times r. And so that means going to be 2 times pi, and the distance I was given is 2.3 times 10 to the 11th meters. And so my circumference ends up being 1.4 times 10 to the 12th meters. Okay, now I can use my distance equals rate times time equation to calculate how long it's going to take me to get all the way around. So the distance I've been given is I've calculated 1.4 times 10 to the 12th meters. I calculated the rate or the velocity down here, so that's going to go in on this side, 2.4 times 10 to the 4th meters per second, and I'm going to multiply that times t. And then when you solve that, divide 1.4 times 10 to the 12th by 2.4 times 10 to the 4th, you end up with 5.8 times 10 to the 7th seconds. And if you wanted an answer that was a little bit more meaningful, you could convert that into years, and that would end up being 1.8 years for Mars to go around the sun. Okay, so that is sample problem example 7.6. I do want to go ahead and look at example 7.7 as well, just to give you another example so you can see how to work it. You will see that, again, the method for doing it is pretty much the same. You have to use the same techniques, recognize that centripetal force is being caused by gravity, and just start manipulating those equations until you get something that you can work with. So in example 7.7, we all know that the orbital period of the Earth is 1 year, or 3.2 times 10 to the 7th seconds. Using this fact, and the fact that the radius of the Earth's orbit around the sun is 1.51 times 10 to the 11th meters, calculate the mass of the sun. Did you ever wonder how they ever came up with that before? How did they come up with the mass of the sun? I mean, you can't take a scale out there and weigh it. So how did they come up with that? Well, they used Newton's law of universal gravitation to calculate this. Okay, so I'm going to get up here what I know so that it's, my information is here. So the period is 3.2 times 10 to the 7th seconds for the Earth. And I know that the distance is 1.51 times 10 to the 11th meters. And I'm asked, what is the mass of the sun? Okay, so again, classic example, I've got one thing orbiting another thing. I've got the Earth orbiting the sun. So once again, I need to say, all right, that tells me gravitational force, the gravitational pull of the sun, is going to be equal to the centripetal force. And you're going to have gravitational, law of universal gravitation, the gravitational constant times the mass of the Earth times the mass of the sun over the distance between them squared is equal to the mass of the Earth times its velocity squared over the distance between them. And this, again, is something that should look very, very familiar to you. We did this in the last problem. The mass of the Earth cancels out. One of the radiuses also cancels out, or distances cancels out. And so that leaves me with G times the mass of the sun over R equals V squared. Okay, now, what do I know? Well, I know R. I know G. The mass of the sun is what I'm trying to find. I don't know the velocity. So how am I going to solve this? Well, I can find the velocity if I know the period and I know the distance, because I know that distance equals rate times time, right? And so therefore, if I can calculate the distance that the Earth travels, so that's going to be the circumference of the circle of the orbit there. So I'm going to have 2 pi r. So that's going to be 2 times pi times 1.51 times 10 to the 11th meters. And so when I solve that, that's going to give me 9.49 times 10 to the 11th meters. Okay, so there's my circumference. There's the distance. The time it takes to get all the way around is 3.2 times 10 to the 7th seconds. So if I use my distance equals rate times time equation again, the distance, 9.49 times 10 to the 11th meters. I don't know the rate, that's what I'm trying to find, but the time is 3.2 times 10 to the 7th seconds. Okay, so then when I divide that, I come up with a rate or a velocity of 3.0 times 10 to the 4th meters per second. Okay, so now that is the same thing as my velocity. So I can take this and I can now plug it into this equation. So I have the gravitational constant, 6.67 times 10 to the minus 11th, Newton meters squared over kilogram squared. Those are really funky units. Mass of the sun is what I'm trying to find out. The distance, 1.51 times 10 to the 11th meters, equals v squared is going to be 3.0 times 10 to the 4th meters per second. I'm going to take that whole quantity and I'm going to square it. So when you crunch through all of this algebra, you square this side, multiply both sides by 1.51 times 10 to the 11th, divide both sides by the gravitational constant. You will end up with, I'm running out of space there, you will end up with a mass of the sun equal to 2.0 times 10 to the 30th kilograms. So that is how those kinds of problems were worked, just by virtue of the fact that if you know some orbital periods, if you know some distances, you can actually calculate the masses of these objects that are orbiting around one another. So you are actually going to have a number of problems to help you practice the different kinds of ways that you're going to have to manipulate these equations using this relationship a lot, using circumference, distance equals rate times time, using those relationships to calculate velocities, putting all of that together. You'll get lots of practice with this and you will get really good at it.